folks, welcome to Vector Calculus. Alright. I've got two arrows right here. You can also call them vectors. Now, if I put these two arrows on the board, you're going to find out that they make a parallelogram. As a matter of fact, we can draw this parallelogram very nicely. So if I go ahead and take my two vectors and I hold them up, well, you may have noticed that I can just shift my first vector, let's call it vector A, so that it meets my second vector here. And I can shift my second vector, let's call it B, so it meets my first vector here. And you can see I've got some kind of a parallelogram shape, right? I've got a parallelogram shape, and that shape encloses some kind of an area. I'd like to know what that area is. And as a matter of fact, I want to know what that area is so much, I'll designate another vector whose magnitude is the amount of this area. What do I mean by that? Well, let me show you. Now instead of one parallelogram, I'm going to give you a bunch. So let's say we have a parallelogram like this. Here's another parallelogram. And here's the ultimate parallelogram. Now clearly there's some differences between these parallelograms. The first parallelogram doesn't take up too much space. Maybe let's say it has an area of 3. The second parallelogram takes up much more space, but still doesn't cover the whole board, for example. So let's say, I don't know, it has an area of 7. And the last parallelogram is really the big one. It's the huge one, right? And let's say it has some area, let's say it has an area of 20, right? Okay, so you see that one parallelogram has an area of 3, another 7, and another 20. Well, I'm going to make a vector. Let's call the vector, I don't know, k, whatever you please. And that vector is going to have a size. And its size is going to reflect the area of the parallelogram. So the size of this vector, let's call this vector k, the magnitude of k is going to be 3. How about this vector? How about the vector that represents this one? Well, let's call it k prime. And the magnitude of this new vector is going to be 7. And finally, I'm going to have a vector represent this parallelogram as well. And of course, this vector is going to be super long, right? It's going to be the biggest of these three vectors because it's going to represent the biggest parallelogram, right? So let's call this k prime prime. And so the magnitude of this largest vector is going to be whatever the area of the parallelogram it represents is. So notice what's going on here, right? This vector is giving me a kind of representative, right? You've got the election playing out now, and every state is sending a representative. Here, every parallelogram is sending a vector to represent how big that parallelogram is. The bigger the parallelogram, the bigger the vector that represents that parallelogram. The bigger the state, the more electoral college votes that represent that state. So for example, this parallelogram has a size of 3, its vector has a size of 3, kind of small. This parallelogram has a size of 7, its vector has a size of 7, kind of medium. This parallelogram has a size of 20, its vector has a size of 20, kind of large, right? So that's what the idea we're trying to capture here is. And you can see, let me get a marker here. There's some more nuance to this idea. Each of these parallelograms is made up of vectors. Here's one, right? Here's one, here's one, here's one, here's one. So all three of these parallelograms are really made up of vectors. Each parallelogram is created by a pair of vectors. Now, here's what we want to do. Here's our goal. Our goal is that given two vectors, we can obviously make a parallelogram, but we want more than that. Given two vectors, let's say we call these vectors A and B. Given these two vectors A and B, we want some kind of an operation on these two vectors that's gonna tell us how big the parallelogram formed by these vectors is. And this operation, we can just call it the cross for now, right? So we can say that there's some kind of operation. We're going to do something with these two vectors A and B, and that something is going to give us the size of the area of the parallelogram. Okay? Now, this operation has a very nice name called the cross product. And the cross product is going to give you, just like we want, it's going to tell us the area formed by two vectors, the area of the parallelogram spanned by two vectors. Let's go ahead and take a look at an example just to see what I mean by that. Okay, so I'm going to erase all of that, but let's keep the last parallelogram here so you can get the idea of what I'm talking about. So let's say I have two vectors, right, A and B. So here's my first vector A. Okay, I'm going to give it some components pretty soon. Here's my second vector B. My first vector A, let's see if I have a dark green marker, and I don't, but that's okay. My first vector A is going to have some components, let's say, I don't know, 2, 1, 0. And my second vector B is going to have some components, 3, 1, 3. How about that? Okay. Now you might notice something. These vectors are in 3D and I'm drawing them on a 2D board, but that's okay. How do I know these vectors are 3D? Because they have three components. One is the X component, the Y component, the Z component. Okay? Now, as you can see, these two vectors create or span a parallelogram. How can we find the area of the parallelogram they span? How can we find the area inside this parallelogram? Look, it's kind of the picture we have down there, right? It's kind of the same picture, just in a different context, if you will. So hold up, let me try to draw this nicely. So there it is. There's vector A and there's vector B. So how do I find that blue area? Well, I have to do something called the cross product. So let's go ahead and do that. So what I have to do is go ahead and first of all just draw these bars. And now what I'm going to do is write I hat, J hat, K hat. Now hopefully you remember that I hat, J hat, and K hat are the three unit vectors for each of the three axes, X, Y, and Z. But if you don't, go ahead and watch our lectures on the direction vectors and everything. And the direction cosines might also be helpful on that. Now, we're going to write our first vector, A, as the second row. Okay, so 2, 1, 0. Let's go ahead and write 2, 1, 0. Where did these numbers come from? They came from the components of our first vector, 2, 1, 0. How about our second vector, B? Well, we can write its components like that. And now I'm going to do something that looks absolutely crazy, right? In fact, there's a name for it, cofactor expansion. But basically what I'm going to do is find the area inside of this thing. And it's a crazy way to do it. But if you just try to digest the idea, then I think you'll be good. So let's go ahead and check out how we can do this cofactor expansion thing. So first thing I'm going to do, let's see if I can get orange up here. So first thing I'm going to do is just imagine there's a kind of a divider here, right? So I'm looking at I hat, and I'm looking at this kind of square. You see this square here? I'm looking at that square. Now, what's the determinant? Don't leave the video if you don't know what that word means. It's a very simple word. What's the determinant of this square matrix? Well, all I'm really asking is, another way to phrase my question is, what is the difference of the product of the diagonals of this matrix? So, to make that even simpler, all we have to say is what is 1 times 3 minus 1 times 0, right? Do you see that? All we're really asking is, what is this diagonal, 1 times 3, minus this diagonal, 1 times 0, okay? And we're going to multiply that by I hat, okay? Multiply all of that by I hat. Okay, well, this is the moment when I wished I had a smartboard, but that's okay. We can go ahead and rewrite that somewhere else. Let's rewrite it here. The magnitude of the cross product is gonna give us this mythical area K, if you will. That kind of an area K. Anyway, let's keep going. What do we do after this? Well, remember, we just did I. We still have two more unit vectors to do, j hat and k hat. So I'm going to write this again, right? Let's go ahead. Where can I write it? Well, I'll just erase this box over here, and hopefully you've taken notes so far, so you don't get stuck, or you can just rewind if necessary. So here's I hat, and we're done with I hat. Remember, we're done with I hat, and now we're moving on to the next unit vector, which is j hat. So what are we going to do with j hat? Okay, so what are we going to do with j hat? Well, with j hat, we're going to do the same thing. Now that we're looking at j hat, I'm going to put these kind of orange bars, and I'm going to circle j hat. That's our focus. And I'm going to look at the two kind of leftover columns that are not in this kind of highlighted orange zone. Those two columns are 2, 3, and 0, 3. Right, and I'm going to find the determinant of those columns. So 2 times 3 minus 0 times 3. So all I have to do right now is find the determinant of these two columns. So how can I do that? Well, much the same way as we did before. Multiply 2 and 3, your first diagonal, and subtract from that the other diagonal, 0 times 3. And to that, we're going to multiply j hat. Okay? And finally, our final concern is k hat. We still have one more unit vector remaining, remember, right? We still have one more unit vector. So let's go ahead and rewrite this. But this time we're going to only highlight the column that k hat is in. So remember, put down your unit vectors, I hat, j hat, k hat, third time. And now let's put on these components 2, 1, and 3, 1 that I erased just so we had some space. So now we're on to the last part. We're on to k hat, okay? In k hat, right? Highlight the row and column that k hat is in. Circle k hat, so you know that's what you're focused on. And this is the kind of matrix you're focused on, right? Yeah, the matrix whose determinant you want to find. So you want to find 2 times 1 minus 1 times 3. And I know it's kind of a crazy formula, but that's how it goes. 2 times 1, that's the product of the first diagonal, minus 1 times 3, product of the second diagonal. And now all we have to do is go ahead and multiply that by k hat. Okay, and now we're almost there. Now all we have to do is put on the signs and simplify. Okay, so can we simplify this a bit? Well, it turns out we can, right? What's 1 times 3? Well, that's just 3 minus 1. So I'm going to have 2 I hat. 6 minus 0 is minus 6 j hat. That minus sign comes from here. 2 minus 3 is just negative 1 k hat. And so that's the vector I'm looking at. That's this k vector, right? Those are the components of my k vector. What are the components? 2, minus 6, and minus 1. If you don't know how I get 2, minus 6, and minus 1 from this notation, go ahead and watch our lecture on vector notation. That's pretty helpful for that. So now what we want to do is find the magnitude of this vector. And what's the magnitude of this thing going to be? Well, use the Pythagorean theorem, right? Use the Pythagorean theorem. And Pythagorean theorem tells you the magnitude of this thing is 2 squared, first component x component squared, plus negative 6 squared, second component y component squared, plus negative 1 squared, third component z component squared. So what does this become? 2 squared becomes 4, negative 6 squared becomes 36, negative 1 squared becomes 1. And so all of this devolves into the square root of 41, and so the magnitude of this vector k is just going to be square root of 41. And so what's the area of our parallelogram going to be? What's the area of this kind of crazy looking parallelogram going to be? Well, it's going to be pretty simple actually. It's just going to be the square root of 41, ladies and gentlemen. And that's really all the cross product is. It's the answer to a simple geometric question. What's the area of a parallelogram? A complicated answer to a simple question. And we'll check you out next time in the next lecture of vector calculus.
Embedded plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.